Welcome to Sleeping Researcher, where science meets tranquility to gently guide you into restful sleep. Here you will find softly narrated journeys through the wonders of the universe, designed to calm your mind and spark your curiosity. Today, we begin a quiet exploration into one of the most intriguing mysteries of physics, the nature of nothingness itself. What is the vacuum of space when it appears to be empty? And yet, even in this seeming void, there exists a subtle energy that shapes our reality in profound ways. This is the world of quantum vacuum energy, a realm where empty space is not truly empty, but alive with tiny fluctuations and possibilities. It challenges our everyday understanding of nothing, inviting us to reconsider what it means to be empty and what it means to be full. Before we journey deeper, if you enjoy this calm and thoughtful narration, please like the video and subscribe to Sleeping Researcher. Your support helps us continue these soothing scientific explorations, perfect for unwinding your day and drifting gently into sleep. So, settle in comfortably, breathe slowly, and prepare to discover the subtle properties of space itself, the silent fabric that holds the cosmos together, and the surprising energy hidden within it. Imagine standing in the vast emptiness of space, far from stars, planets, or any matter. At first glance, this might seem like the purest form of nothing, a perfect void, devoid of substance or energy. Yet, when we delve into the physics that govern our universe, this intuitive notion of nothingness begins to unravel. What appears as empty space is, in fact, a seething, dynamic stage where mysterious forces and particles flicker in and out of existence. This paradox challenges our everyday understanding and invites us to explore the true nature of nothing. It is within this seemingly barren expanse that the quantum vacuum reveals its surprising and profound properties, reshaping how we perceive the fabric of reality itself. The term vacuum in physics differs greatly from the common idea of an empty void. Rather than a simple absence, the vacuum represents the lowest possible energy state of a quantum field. Even in this ground state, the vacuum is not silent. It is alive with ephemeral fluctuations. These fluctuations arise from the inherent uncertainty that lies at the heart of quantum mechanics, leading to the continual creation and annihilation of virtual particles. These particles cannot be observed directly, yet their presence influences measurable phenomena, such as the Casimir effect, which manifests as a tiny force between uncharged metal plates in a vacuum. Thus, the vacuum is more accurately described as a restless medium brimming with latent energy and potential. The energy contained within this quantum vacuum, known as vacuum energy, has profound implications both theoretically and cosmologically. Vacuum energy contributes to the cosmological constant, a term introduced by Einstein to explain the observed acceleration in the expansion of the universe. This suggests that what we consider empty space carries an intrinsic energy density, influencing the large-scale structure and destiny of the cosmos. Despite its subtlety, vacuum energy is a fundamental ingredient in our universe's makeup, linking the microcosmic world of quantum fields with the vast expanse of cosmic evolution. This connection inspires ongoing research as scientists endeavor to better understand how the properties of space itself emerge from such quantum underpinnings. Moreover, the properties of space as revealed by quantum vacuum energy challenge the classical notion of a passive backdrop to physical events. Instead, space behaves as an active participant, possessing qualities such as elasticity and the ability to store and release energy. These characteristics not only influence particle physics, but also shape phenomena like Hawking radiation near black holes, where the vacuum's fluctuations can lead to the emission of particles from the event horizon. This dynamic view of space as a vibrant, energetic medium expands our comprehension beyond the limits of classical physics, inviting us to rethink the fundamental nature of reality. Such insights open the door to deeper questions about the origin of space and time themselves. For centuries, the classical view of space was simple and intuitive. It was seen as an empty, passive void, a vast nothingness stretching endlessly between stars, planets, and matter. In this perspective, space provided a stage on which the drama of the universe unfolded, but it itself had no features or influence. Newtonian physics, which dominated scientific thought for over 3 centuries, treated space as absolute and unchanging. It was a fixed, empty container in which objects moved and forces acted, yet it contributed nothing to the dynamics within it. This idea was deeply rooted in everyday experience, where space appears to be just a silent, invisible expanse without substance or energy. Within this framework, the vacuum was defined as a perfect emptiness, devoid of matter, energy, or any physical properties. Its role was that of a neutral backdrop, silent and still, waiting for matter or radiation to pass through or occupy it. The vacuum's emptiness was not questioned. It was simply accepted as the natural state of space, a concept that seemed to align perfectly with human intuition and classical mechanics. The classical conception of empty space also extended into the realm of electromagnetism, where space was considered a medium lacking any inherent structure. Early scientists speculated about a luminiferous ether, a hypothetical substance thought to fill space and carry light waves. But experiments failed to detect this ether, reinforcing the idea of space as a void. Later, Einstein's theory of relativity further transformed the understanding of space and time, merging them into a dynamic fabric known as space-time. Yet, even in this revolutionary framework, empty space was often treated as a mere geometric stage, curved by mass and energy, but itself largely inert. This geometric view maintained the impression that space, though malleable, remained fundamentally empty and passive, a silent entity shaped by the presence of matter, but not contributing actively beyond its curvature. The vacuum was still considered a region lacking any intrinsic energy or activity. a blank canvas upon which gravity and motion played out their roles. It wasn't until the advent of quantum mechanics in the early 20th century that the classical view of empty space began to change dramatically. Quantum theory introduced the idea that even a perfect vacuum is not truly empty, but rather seething with ephemeral activity. At microscopic scales, the vacuum is a restless ocean of fleeting particles and antiparticles that spontaneously appear and vanish in accordance with the uncertainty principle. These quantum fluctuations imbue the vacuum with a subtle energy known as quantum vacuum energy, which classical physics never anticipated. This revelation challenged the long-held assumption of space as a passive void, showing instead that the vacuum possesses a dynamic structure and energy content. The classical concept of emptiness gave way to a more complex and vibrant understanding, where the vacuum plays an active role in the fabric of reality itself. The implications of this shift are profound. Whereas classical physics saw space as empty and inert, modern physics reveals it as a seething, energetic medium with intrinsic properties. Quantum vacuum energy influences the behavior of particles, contributes to forces such as the Casimir effect, and even affects the expansion of the universe through what we call dark energy. This new perspective transforms our understanding of nothingness. It is no longer a simple void, but a dynamic arena full of potential and subtle interactions. Space, it seems, is as much a participant in the cosmic dance as the particles and fields it contains. A realization that continues to inspire new theories and investigations into the nature of reality itself. As we move beyond the classical view, we begin to see space not as a silent emptiness, but as a fundamental player in the unfolding story of the cosmos. When quantum mechanics first emerged in the early 20th century, it introduced a revolutionary concept that challenged our deepest assumptions about the nature of reality. Unlike classical physics, which treated empty space as a simple void, devoid of substance, quantum theory proposed that even the vacuum is alive with activity. This seemingly paradoxical idea arises from the principles of quantum field theory, where fields permeate all of space, and fluctuations within these fields give rise to transient particles and energy. These fleeting phenomena, often called vacuum fluctuations, imply that nothingness is not truly empty, but rather a restless, dynamic state. This insight opened the door to a universe far stranger and more intricate than previously imagined, where the vacuum itself possesses physical properties that can influence matter and energy in subtle ways. It is within this framework that physicists began to explore the enigma of quantum vacuum energy, a concept that continues to intrigue and inspire scientific inquiry today. The quantum vacuum is often described as a sea of virtual particles, spontaneously appearing and disappearing in accordance with the uncertainty principle. These virtual particles are not particles in the usual sense. Rather, they are temporary excitations of underlying quantum fields that cannot be directly observed, but have measurable effects. For instance, the Casimir effect demonstrates how two uncharged, parallel metal plates placed very close together experience an attractive force due to alterations in the vacuum energy between them. This phenomenon provides tangible evidence that the vacuum is an active participant in physical processes rather than a passive backdrop. Such subtle interactions reveal a layered complexity to space, suggesting that what appears to be empty is actually filled with a fluctuating energy that can influence forces, particles, and even the geometry of space-time itself. Furthermore, quantum vacuum energy plays a surprising role on cosmic scales, connecting the physics of the very small with the behavior of the entire universe. Observations of the accelerated expansion of the cosmos point to a mysterious energy permeating all space. Dark energy, which some theorists associate with vacuum energy. Although the exact nature of dark energy remains elusive, its discovery underscores the profound significance of the vacuum's intrinsic properties. This cosmic connection highlights how the quantum vacuum is not merely a curiosity confined to microscopic phenomena, but a fundamental element shaping the universe's evolution. In this light, space itself emerges as a rich and active medium, a stage where quantum fluctuations ripple outward to influence the grandest structures and destinies. The recognition that vacuum energy is woven into the fabric of reality has inspired new approaches in physics, from attempts to unify quantum mechanics and gravity to explorations of the multiverse. Researchers continue to probe the vacuum's mysteries, using advanced experiments and theoretical models, seeking to understand how these ephemeral energies might relate to the fundamental forces and particles we observe. Each discovery reveals deeper layers of complexity and subtlety, reminding us that the vacuum is not simply a void, but a wellspring of potential. As quantum mechanics invites us to reconsider the nature of emptiness, we find ourselves drawn into a realm where space is alive with unseen phenomena, hinting at a universe more interconnected and profound than our senses might suggest. At first glance, empty space might seem devoid of anything at all, a perfect void where nothing exists. Yet, quantum physics reveals a far more intricate picture, where even the emptiest regions teem with subtle activity. This phenomenon is known as quantum vacuum energy, a kind of fluctuating energy that pervades the very fabric of space. It arises from the principles of quantum mechanics, which tell us that energy and matter can never be completely still or absent, even in a vacuum. Instead, pairs of particles and antiparticles spontaneously emerge and vanish in fleeting moments, creating a restless background hum of existence. These vacuum fluctuations represent a foundational aspect of reality, one that challenges our classical intuition about emptiness and invites us to explore the unseen dynamics beneath the surface of space itself. The concept of vacuum energy is not merely a theoretical curiosity. It carries profound implications for our understanding of the universe. It suggests that space is an active participant in physical processes, capable of storing and releasing energy, This idea underpins phenomena such as the Casimir effect, where two uncharged metal plates placed closely together experience an attractive force due to alterations in vacuum fluctuations between them. Such experiments provide glimpses into the tangible consequences of vacuum energy, offering windows into the quantum nature of space and hinting at the deep connections between energy, matter, and geometry. Understanding quantum vacuum energy invites us to explore the subtle interplay between the quantum world and the vastness of space, blurring the boundaries between emptiness and existence. It challenges us to expand our conceptual frameworks, embracing a vision of reality where the vacuum is not an inert backdrop, but a vibrant stage for the unfolding drama of nature. As research advances, new theoretical insights and experimental techniques continue to illuminate the profound properties of space, encouraging a deeper appreciation for the mysterious energies that underlie all things. This journey into the quantum vacuum sets the stage for further inquiry into the nature of space itself, its geometry, and the forces that govern the cosmos. With each step, we move closer to unraveling the enigma of the vacuum, poised to uncover how these subtle energies connect to the broader tapestry of physical laws and the universe's grand design. Within the restless sea of quantum vacuum energy, virtual particles emerge as fleeting manifestations of the universe's subtle dynamism. These ephemeral entities appear as pairs, one particle and its corresponding antiparticle, materializing momentarily before annihilating each other and fading back into the void. They are not particles in the traditional sense, but rather transient fluctuations permitted by the uncertainty principle, which allows energy to be borrowed from the vacuum for brief intervals. This dance of appearance and disappearance gives rise to what might be called flickering ghosts, elusive phenomena that defy direct observation, yet leave measurable imprints on the physical world. Through their brief existence, virtual particles challenge our classical notions of emptiness and invite us to envision space as a vibrant, ever-changing stage where matter and energy continually interplay. These virtual pairs contribute to various quantum effects and subtly influence forces and interactions at the smallest scales. Their presence is woven into the fabric of reality, shaping the way particles behave, how forces propagate, and even how the vacuum itself exerts influence on matter. In this way, the invisible universe becomes tangible, revealing that beneath the apparent stillness of empty space lies a ceaseless flickering of creation and destruction, a reminder that nothing is never truly empty. The existence of virtual particles transcends theoretical musings, finding expression in concrete physical phenomena that have been experimentally verified. One striking example is the Lamb shift, a subtle change in the energy levels of electrons within hydrogen atoms, caused by interactions with vacuum fluctuations. Similarly, the anomalous magnetic moment of the electron, a tiny deviation from classical predictions, arises from the influence of virtual particles swirling in the quantum vacuum. These delicate effects underscore the profound impact that transient virtual particles exert on the properties of matter and the fundamental constants of nature. Through precise measurements and sophisticated calculations, physicists have confirmed that these ghostly pairs, though fleeting, are indispensable to the coherence and consistency of quantum field theories. Their role extends further, providing a framework for understanding the forces that govern particle interactions, such as the electromagnetic, weak, and strong forces. Virtual particles mediate these forces by popping in and out of existence, transmitting energy and momentum in a manner that defines the interactions we observe. In this sense, the vacuum itself becomes an active participant, a medium teeming with potentiality that sustains the subtle architecture of the cosmos. Beyond their influence on particle physics, virtual particles also contribute to intriguing macroscopic effects that bridge the quantum and classical worlds. The Casimir effect, for instance, arises when two closely spaced metal plates experience an attractive force due to changes in vacuum fluctuations between them. Here, the presence of the plates alters the spectrum of virtual particle pairs that can exist in the intervening space, creating an imbalance that results in a measurable force. This phenomenon vividly demonstrates how the vacuum is not merely an empty void, but a dynamic environment whose properties can be shaped by boundary conditions and geometry. Such experiments lend tangible evidence to the existence of virtual particles, allowing us to grasp the otherwise intangible nature of the quantum vacuum. By exploring these subtle interactions, scientists continue to uncover new ways in which the flickering ghosts of the vacuum influence material reality, reminding us that the quantum realm is inextricably linked to the structure and behavior of the space we inhabit. The fleeting existence of virtual particles also hints at profound connections between quantum mechanics and gravity, inviting speculation about the very nature of space and time. Some theoretical frameworks propose that the vacuum fluctuations of virtual particles contribute to the energy density of empty space, a concept closely related to the cosmological constant that governs the expansion of the universe. Although these ideas remain under active investigation, they suggest that the restless activity of virtual particles might play a role in shaping the large-scale geometry of the cosmos. In this light, the flickering ghosts become more than mere curiosities. They emerge as fundamental actors in the unfolding story of the universe itself. As physicists strive to reconcile quantum theory with general relativity, the mysterious behavior of virtual particles continues to inspire new insights, pointing toward a deeper understanding of space as a dynamic, interactive arena where the quantum and cosmic realms converge. Contemplating virtual particles as the flickering ghosts of the vacuum encourages us to rethink our relationship with the concept of emptiness. Rather than a passive backdrop, the vacuum reveals itself as a lively, restless medium, alive with transient possibilities and hidden energies. These ephemeral pairs embody the subtle interplay of creation and annihilation, reflecting a universe in constant flux, even in the quietest corners of space. As we continue to explore this enigmatic domain, we are reminded that the fabric of reality is woven from the delicate threads of quantum fluctuations, inviting us to listen closely to the whispered secrets of the vacuum. This awareness sets the stage for deeper inquiry into the nature of space itself, its geometry, and the forces that govern the cosmos, leading us further into the profound mysteries that lie beyond the flickering ghosts. At the heart of quantum mechanics lies Heisenberg's uncertainty principle, a fundamental truth that reshapes our understanding of measurement and reality itself. This principle tells us that certain pairs of physical properties, such as position and momentum, cannot both be known with absolute precision at the same time. The more precisely one property is measured, the less precisely the other can be determined. While this might seem like a limitation, it reveals a profound aspect of nature, a built-in fuzziness that permeates the very fabric of existence. This intrinsic uncertainty extends beyond particles and waves, reaching into the void we call empty space. Rather than an absolute nothingness, the vacuum is subject to these quantum uncertainties, allowing for momentary fluctuations in energy that give rise to transient phenomena. These fluctuations manifest as brief appearances and disappearances of particle-antiparticle pairs, a direct consequence of the uncertainty principle's allowance for energy variations within incredibly short timeframes. In this way, the vacuum itself becomes a dynamic arena where energy momentarily blinks into being, only to vanish again, a perpetual dance dictated by the limits of quantum certainty. These vacuum fluctuations are not mere theoretical curiosities, but have measurable effects that ripple through the cosmos. For example, the Casimir effect, observed as a measurable force between two closely spaced metal plates, arises from the alteration of vacuum energy between the plates compared to outside them. This subtle pressure is a tangible consequence of the vacuum's restless nature, demonstrating that what we perceive as empty space possesses a complex structure shaped by quantum laws. The fleeting existence of virtual particles also influences phenomena such as the Lamb shift, a tiny energy difference in hydrogen atoms that classical physics cannot explain without accounting for vacuum fluctuations. This interplay between uncertainty and vacuum activity reveals a universe where emptiness is, paradoxically, a seething backdrop of potentiality, where energy and matter are continuously birthed and reabsorbed in a ceaseless cycle. In this light, the vacuum emerges not as a void, but as a foundational stage for all physical processes, its energetic fluctuations underpinning the forces and particles that compose our reality. The implications of Heisenberg's uncertainty principle extend further to the very geometry and expansion of space. Quantum vacuum energy, often referred to as zero-point energy, imbues space with a subtle pressure that may influence the large-scale structure of the universe. Cosmologists link this vacuum energy to the mysterious dark energy a force accelerating cosmic expansion, suggesting that the restless quantum vacuum plays a role far beyond the microscopic realm. Through this lens, space is not an inert container, but an active participant in cosmic evolution, its quantum properties guiding the unfolding of the universe itself. The spontaneous creation and annihilation of energy within the vacuum hint at a profound connection between the smallest scales of quantum mechanics and the grandest scales of cosmology. As we delve deeper, we begin to see that the vacuum's energy is not simply a background hum, but a vital component shaping the destiny of everything we observe. This quantum perspective invites us to reconsider the nature of nothingness and the essence of space as a physical entity. Far from being empty, the vacuum is a reservoir of fluctuating energies, a complex and active medium that challenges classical intuition. The interplay of uncertainty and vacuum fluctuations suggests that space itself is imbued with latent power, a canvas on which the patterns of reality are continuously sketched and erased. These insights deepen our appreciation for the delicate balance between order and chaos that defines the quantum world, revealing a subtle harmony beneath apparent randomness. In this ongoing dance of energy and emptiness, the vacuum becomes a source of creation, a silent architect shaping the quantum stage on which matter and forces emerge. This understanding opens a path toward exploring the geometry and forces woven into space, guiding us gently toward the next chapter of cosmic discovery. Among the most striking manifestations of quantum vacuum energy is the Casimir effect, a phenomenon that elegantly reveals how empty space can exert a tangible force. Imagine placing two uncharged, perfectly conducting plates just a few nanometers apart within a vacuum. Classical physics would suggest that nothing significant occurs between them, as no particles or fields are present. Yet, quantum theory predicts that the vacuum between these plates is teeming with ephemeral fluctuations, virtual particles spontaneously appearing and disappearing in accordance with the uncertainty principle. These fluctuations are not uniform. The plates impose boundary conditions that restrict the wavelengths of virtual particles that can exist in the intervening space, effectively creating a difference in the vacuum energy density inside and outside the gap. This imbalance generates a minute but measurable pressure, gently pushing the plates together. This counterintuitive force arises purely from the properties of the vacuum itself, a testament to the profound reality that nothingness in the quantum realm is far from empty. The Casimir effect transcends theoretical curiosity, emerging as one of the few experimentally verified phenomena, providing direct evidence of quantum vacuum energy's physical influence. Precision experiments using sensitive microelectromechanical systems have measured the attraction between plates separated by distances on the order of tens of nanometers, in remarkable agreement with theoretical predictions. This concordance between theory and observation grounds the abstract concept of vacuum fluctuations within the fabric of measurable reality. It also bridges the gap between the invisible quantum world and the macroscopic scales accessible to human instruments. By demonstrating that the vacuum can exert forces that influence matter, the Casimir effect challenges our classical notions of space as a passive backdrop, revealing it instead as an active participant in the dynamics of the universe. These insights invite deeper contemplation of the vacuum's role in fundamental physics, from the stability of matter to the origins of forces. Beyond its experimental significance, the Casimir effect offers intriguing implications for the geometry and topology of space itself. Since the force depends sensitively on the shape, size, and material properties of the boundaries confining the vacuum fluctuations, it reflects how space can be sculpted by matter and vice versa. This interplay hints at a more profound connection between quantum fields and the structure of space-time, suggesting that the vacuum is not merely a static stage, but a dynamic entity shaped by and shaping the objects it envelops. Such considerations have inspired speculative explorations into harnessing vacuum energy for nanoscale technologies, as well as informing theoretical models that attempt to unify quantum mechanics with gravity. In this light, the Casimir effect stands as a subtle reminder that even the quietest corners of the cosmos harbor forces born from the restless energy of nothingness. It beckons us to explore further how the vacuum's hidden pressures might influence phenomena on scales both vast and minute. As we ponder the Casimir effect, we begin to glimpse the profound layers beneath the apparent emptiness of space. The vacuum energy that nudges these plates is but one facet of a broader cosmic mosaic, where quantum fields weave a dynamic tapestry underpinning all physical existence. This phenomenon encourages us to view the vacuum not as a void, but as a reservoir of potential, capable of exerting influence and shaping reality in subtle yet fundamental ways. The forces born of quantum fluctuations challenge the boundary between something and nothing, inviting us to reconsider the essence of the space that surrounds us. In this quiet, persistent push of the vacuum, we find a whisper of the deeper principles that govern the universe, guiding our journey into the mysteries that lie ahead. When we speak of space, it is tempting to imagine a vast emptiness, a silent void stretching infinitely in every direction. Yet, modern physics reveals a far more intricate picture. Space is not merely an empty container within which matter and energy reside. Rather, it is an active, dynamic medium with its own set of properties and behaviors. At the heart of this understanding lies the concept of the quantum vacuum, a state that, while devoid of particles in the classical sense, teems with fluctuating energy and transient phenomena. These fluctuations arise from the uncertainty principle, which forbids any region of space from being perfectly still or completely empty. Instead, space itself vibrates with ephemeral particles, momentarily flickering into and out of existence, a restless dance of creation and annihilation. This perspective invites us to reimagine space, not as a passive backdrop, but as a vital participant in the unfolding drama of the cosmos. The quantum vacuum energy that permeates space is a subtle yet profound manifestation of this dynamic nature. It is a baseline energy that persists even in the absence of matter or radiation, an intrinsic feature of the vacuum itself. This energy gives rise to measurable effects, such as the Casimir force that gently pushes objects together across empty space and plays a crucial role in the evolution of the universe. On cosmic scales, vacuum energy is linked to the mysterious phenomenon known as dark energy, which appears to drive the accelerated expansion of the cosmos. Thus, what we once thought of as nothingness becomes a reservoir of potential that shapes the large-scale structure and destiny of the universe. By embracing this view, we step beyond the simplistic notion of emptiness and begin to appreciate space as a rich, complex medium imbued with the power to influence matter, energy, and even the fabric of space-time itself. This dynamic quality of space also underpins the very nature of fields. The invisible entities that fill the cosmos and mediate forces between particles. Quantum field theory describes how each fundamental force is associated with a field that exists everywhere, even in the vacuum. The vacuum then is not a void, but a stage where these fields continuously fluctuate, their inherent energy shaping interactions at the smallest scales. These fluctuations can have tangible consequences. They contribute to the masses of particles, affect the stability of atomic structures, and even influence the conditions in the early universe. Space, far from being inert, is alive with activity at every moment, a vast ocean of energy and possibility that both constrains and enables the physical phenomena around us. In this view, the fabric of space can bend, stretch, and ripple, responding to the presence of energy and matter in a dynamic interplay described by Einstein's theory of general relativity. Yet beyond gravity, the quantum vacuum adds a layer of complexity that challenges our classical intuitions. It reveals a universe where emptiness is charged with potential, where the tiniest fluctuations can ripple outward to influence the grandest cosmic structures. This dynamic medium is not static, but constantly evolving, a silent but persistent force that shapes the very essence of reality. By embracing space as an active participant, we unlock new ways of understanding the cosmos, revealing its subtle interconnectedness and the delicate balance that sustains it. The concept of vacuum energy emerges from the quantum world, where empty space is far from empty. Instead, it teems with fleeting particles and fluctuating fields, a restless sea of activity beneath what appears to be nothingness. These quantum fluctuations give rise to a tiny but persistent energy known as vacuum energy. This energy is not localized, but rather an intrinsic property of space itself, woven into its very fabric. When physicists attempt to calculate the amount of vacuum energy predicted by quantum theory, they find results that are staggeringly large, far greater than what we observe in the cosmos. This discrepancy is one of the most profound puzzles in modern physics. Yet, despite its elusive nature, vacuum energy is believed to exert a subtle pressure on space, influencing the universe on the largest scales. This influence of vacuum energy is intimately connected to the cosmological constant, a term introduced by Albert Einstein in his equations of general relativity. Originally conceived as a way to achieve a static universe, the cosmological constant represents a uniform energy density filling space, exerting a repulsive force that counteracts gravity. For decades, this constant was thought to be zero or negligible until observations of distant supernovae in the late 20th century revealed that the universe's expansion is actually accelerating. This surprising discovery suggested that vacuum energy, or a form of dark energy represented by the cosmological constant, is pushing space itself apart. This acceleration implies that the vacuum is not merely a passive backdrop, but a dynamic player, shaping the universe's large-scale structure and destiny. The effects of vacuum energy on cosmic expansion are profound. As space expands, the vacuum energy density remains constant per unit volume, causing the total energy associated with vacuum to increase. This counterintuitive property means that, unlike matter and radiation, which dilute as the universe grows, vacuum energy grows in influence. Over vast timescales, this leads to an ever faster expansion, stretching space and isolating galaxies from one another. The balance between gravitational attraction and vacuum energy repulsion determines the ultimate fate of the cosmos, whether it will continue to expand forever, slow down, or undergo more exotic scenarios. Our current understanding suggests a future dominated by this mysterious energy, where the universe becomes a vast, cold, and lonely expanse. Exploring vacuum energy also challenges our comprehension of space and time. The quantum vacuum blurs the boundary between emptiness and substance, hinting at a deeper layer of reality, where space is not merely a stage, but an entity capable of its own dynamics. This realization invites new perspectives on the fundamental forces and fields that govern existence, and on the enigmatic nature of dark energy itself. It also connects cosmology with quantum mechanics, two pillars of physics that often seem at odds. By studying vacuum energy and the cosmological constant, scientists hope to uncover clues that might unify these theories, revealing a more complete picture of the universe's origin, evolution, and ultimate fate. contemplate the subtle energy permeating the vacuum, we begin to appreciate the delicate interplay between the smallest scales of quantum fluctuations and the grand expanse of cosmic history. This interplay reminds us that the universe is an intricate tapestry, where the invisible threads of vacuum energy weave through space-time, shaping the flow of cosmic time itself. Understanding this link not only deepens our grasp of fundamental physics, but also opens doors to new questions about the nature of reality, inspiring ongoing exploration into the mysteries of the cosmos. With this in mind, we turn our attention to the remarkable properties of space itself and how vacuum energy continues to influence its ever-changing landscape. In the vast emptiness of space, the concept of nothing takes on a curious, new meaning. Far from a simple void, the quantum vacuum is a seething background of fluctuating energy, where particles pop in and out of existence in fleeting moments. This restless activity arises from the principles of quantum mechanics, which dictate that even the emptiest space is never truly empty. Instead, it is filled with what is known as vacuum energy, a subtle and pervasive presence that defies classical expectations. This energy is not something we can touch or see, yet it exerts a profound influence on the fabric of space-time itself. As we peer deeper into the cosmos, observations reveal that the universe's expansion is accelerating, suggesting the presence of a mysterious force pushing galaxies apart. Scientists have named this enigmatic influence dark energy, and one leading hypothesis is that it may be connected to the vacuum energy embedded in the quantum vacuum. This connection invites us to reconsider the nature of space, not as a passive arena, but as an active participant in cosmic evolution. The concept of vacuum energy challenges our classical intuition, as it implies that empty space possesses an intrinsic energy density. According to quantum field theory, every point in space is a stage for virtual particles and fields, whose zero-point energies contribute to this vacuum energy. Although individually imperceptible, their collective effect could be immense, influencing the expansion rate of the universe on the largest scales. Yet, when physicists attempt to calculate the magnitude of vacuum energy using known quantum mechanics, the predicted values overshoot observations by an astonishing factor. This profound discrepancy, often referred to as the cosmological constant problem, remains one of the most significant puzzles in modern physics. Nevertheless, the idea that vacuum energy might drive the accelerated expansion imbues the cosmos with a quiet dynamism, suggesting that nothingness is far more complex and vital than previously imagined. It is as if the universe possesses a hidden reservoir of energy, gently but inexorably guiding its fate. Exploring the physics of vacuum energy also draws us into deeper questions about the structure and properties of space-time. If vacuum energy truly permeates all of space, it may affect the curvature and geometry of the universe, influencing how matter and light move through the cosmos. This perspective aligns with Einstein's general theory of relativity, where energy and mass determine the shape of space-time. Yet, vacuum energy is unique in that it exhibits a negative pressure, a kind of repulsive force that counteracts gravity on cosmic scales. This repulsion manifests as dark energy's accelerating effect, a subtle push that grows stronger as the universe expands. Such behavior challenges our understanding of fundamental forces and invites us to rethink the delicate balance that governs cosmic evolution. The interplay between vacuum energy and space-time thus remains a rich field of inquiry, bridging the quantum world and the vast cosmic landscape. As we contemplate the mysterious driver behind the universe's accelerating expansion, we are reminded of the profound enigma posed by dark energy. Its true nature remains elusive, a whisper from the depths of the cosmos that beckons scientists to explore beyond the known frontiers of physics. Whether vacuum energy fully accounts for dark energy, or if new physics awaits discovery, the journey toward understanding continues to inspire awe and wonder. This pursuit not only illuminates the properties of space itself, but also challenges us to imagine realities beyond our current grasp. In the next step of our exploration, we will delve further into the fascinating interplay between quantum fields and cosmic evolution, seeking to uncover the subtle mechanisms that shape the universe's grand destiny. Even in the most tranquil corners of the cosmos, where temperatures approach absolute zero and matter seems to rest in perfect stillness, a subtle and persistent energy lingers. This is zero-point energy, the lowest possible energy state that a quantum system can possess. Contrary to classical intuition, the vacuum of space is far from empty. It is a seething landscape of fluctuating quantum fields, never completely at rest. These fluctuations arise because, according to the uncertainty principle, the energy of a system cannot be precisely zero. Instead, particles and antiparticles momentarily wink into and out of existence, a restless dance that permeates all of space. This pervasive energy, inherent to the vacuum itself, challenges our conventional understanding of nothingness and reveals the quantum strangeness that underpins the fabric of reality. The persistence of vacuum energy, even at absolute zero, highlights the deeply counterintuitive nature of quantum physics. While classical physics would predict that all motion ceases at this ultimate temperature, quantum mechanics assures us that fluctuations endure. These zero-point oscillations are not mere theoretical curiosities. They have measurable consequences. For example, the Casimir effect, a subtle force observed between closely spaced metal plates in a vacuum, emerges precisely because of these vacuum fluctuations. Here, the energy difference between the plates and the surrounding space creates an attractive force, providing tangible evidence that the vacuum is a dynamic entity rather than a void. Such phenomena underscore the fact that space itself possesses intrinsic properties shaped by the restless energy of quantum fields. This ever-present vacuum energy also plays a crucial role in the evolution of the cosmos. In the earliest moments after the Big Bang, Fluctuations in quantum fields may have seeded the large-scale structures we observe today, such as galaxies and clusters. Moreover, the concept of zero-point energy extends into the realm of cosmology, where it forms a foundational element in attempts to understand dark energy, the mysterious force driving the accelerated expansion of the universe. Though the precise relationship between vacuum energy and dark energy is still under active investigation, the idea that empty space harbors a latent energy challenges our perceptions and opens new avenues for exploring the universe's deepest mysteries. As we continue to probe the nature of vacuum energy, we confront profound questions about the very nature of space and time. Is the vacuum a simple backdrop for cosmic phenomena, or does it possess a complex structure woven from quantum fields and energy fluctuations? The answers may lie in the interplay between quantum mechanics and gravity, a frontier where current theories strive to reconcile the large and the small. Exploring zero-point energy not only enriches our understanding of quantum theory, but also invites us to consider the fundamental properties that define the cosmos. In this quiet energy, the whispers of the universe's underlying fabric become perceptible, urging us to listen closely to what space itself might reveal. In the realm of particle physics, vacuum energy takes on a surprisingly tangible role. Far from being an empty void, the vacuum is a seething landscape of ephemeral particles and fluctuating fields, continually bubbling with what is known as zero-point energy. These quantum fluctuations, though fleeting and subtle, have measurable consequences, influencing the masses of particles and the forces that govern their interactions. For instance, the Higgs field, permeating all space, imparts mass to fundamental particles, and its behavior is intimately connected to vacuum energy. This connection reveals that the vacuum is not merely a passive stage, but an active player in shaping the properties of matter itself. Delving deeper, the vacuum energy affects the strength and behavior of the fundamental forces, such as the electromagnetic, weak, and strong nuclear forces. These interactions are mediated by particles called gauge bosons, whose characteristics depend on the vacuum's structure. Quantum chromodynamics, the theory describing the strong force, illustrates how vacuum fluctuations contribute to the binding of quarks within protons and neutrons, providing mass and stability to atomic nuclei. This intricate dance between vacuum fields and particles bridges microscopic quantum phenomena with the observable properties of matter, revealing a profound unity within nature's laws. The vacuum, in this sense, becomes a dynamic medium through which forces are not just transmitted, but also shaped. Beyond particle masses and forces, vacuum energy plays a crucial role in connecting the quantum world with cosmology. The energy density of the vacuum, though minuscule on small scales, accumulates across the vastness of space, contributing to the universe's expansion and large-scale structure. This enigmatic contribution is often referred to as dark energy, a mysterious force driving cosmic acceleration. Here, the microcosm and macrocosm meet as quantum vacuum fluctuations influence the destiny of galaxies and the fate of the cosmos itself. Understanding how vacuum energy operates across these scales challenges physicists to weave together quantum mechanics and general relativity in a seamless framework. This profound relationship between vacuum energy and particle physics invites us to reconsider the nature of nothingness. Instead of emptiness, the vacuum emerges as a dynamic, energetic canvas, imbued with the potential to create and transform. The particles and forces we observe arise from this restless quantum background, suggesting that space itself holds the key to understanding existence. As we explore these ideas, we glimpse the subtle threads binding the minuscule world of particles to the grand architecture of the universe. The physics of nothing, then, becomes a gateway to the deepest questions about reality. As we continue to unravel the mysteries encoded in vacuum energy, new questions surface about the unification of forces and the ultimate fabric of space-time. Quantum vacuum fluctuations hint at phenomena beyond the standard model, inspiring theories that seek to explain dark matter, neutrino masses, and the early moments of the universe. The vacuum's restless energy is both a challenge and a guide, leading researchers toward a more complete understanding of nature's laws. In the quiet stillness of space, the quantum vacuum hums with possibilities, inviting us to explore further the subtle connections that govern both the smallest particles and the vast cosmos. At the heart of understanding the vacuum lies quantum field theory, a profound framework that redefines what we mean by nothing. Unlike the classical notion of empty space as a mere void, quantum field theory reveals a dynamic fabric where fields permeate all of space and time, constantly fluctuating in a restless dance. These fluctuations are not random noise, but are governed by precise mathematical laws. Each quantum field corresponds to a fundamental particle, and even in its lowest energy state, the vacuum, these fields never truly rest. This perpetual activity gives rise to vacuum fluctuations, ephemeral bursts of energy that briefly manifest as particle-antiparticle pairs before annihilating back into the vacuum. Such phenomena challenge our classical intuitions, showing that the vacuum is better described as a seething quantum medium rather than an empty backdrop. The mathematics of quantum field theory provides the language to describe these ephemeral processes, using complex functions and operators to capture the probabilities and interactions of quantum fields. Central to this framework is the concept of the vacuum state, which, far from being a static baseline, is a sea of virtual particles and zero-point energies. These zero-point energies represent the irreducible energy present, even when all measurable particles have been removed. While these energies are minuscule on everyday scales, They have profound implications in cosmology and particle physics, influencing phenomena such as the Casimir effect and the accelerating expansion of the universe. The calculations that predict these effects stem from the rigorous application of quantum field theory's mathematical tools, illustrating how abstract equations translate into observable physical consequences. Quantum vacuum energy also plays a crucial role in shaping the structure of space-time itself. According to the principles of general relativity, energy and momentum influence the curvature of space-time, and thus the vacuum's energy density contributes to the universe's overall geometry. This interplay raises deep questions about the cosmological constant, a term introduced by Einstein to describe the vacuum's energy density and its effect on cosmic expansion. Despite decades of research, the exact value of vacuum energy predicted by quantum field theory vastly exceeds what is observed astronomically, a discrepancy known as the cosmological constant problem. This tension between theory and observation remains one of the most profound challenges in modern physics, driving ongoing research into the nature of space, time, and the vacuum itself. Through quantum field theory, physicists have developed a language that captures the subtleties of the vacuum and its fluctuations, allowing for a deeper appreciation of the nothingness that underpins reality. This framework not only explains the vacuum's restless energy, but also connects it to fundamental forces and particles, bridging quantum mechanics and relativity in subtle ways. As we delve further into these mathematical descriptions, we uncover hints of new physics beyond our current models, possibilities that may illuminate the nature of dark energy, the origin of mass, and the unification of forces. The language of quantum fields transforms our understanding of space from a passive stage into a living entity, rich with activity and potential. With this foundation in quantum field theory, we are poised to explore more deeply the enigmatic properties of space and the vacuum's role in the cosmic story. The subtle interplay of fields and fluctuations invites us to reconsider the fabric of reality itself, opening pathways toward new insights in both theoretical and experimental physics. As the mathematical language continues to evolve, it guides us toward a more complete picture of the universe's fundamental nature, where nothing is truly empty and every moment holds within it the whisper of creation. In the quiet depths of physics laboratories around the world, researchers are embarking on delicate experiments that seek to measure the elusive energy permeating the vacuum of space. Known as vacuum energy or quantum vacuum fluctuations, this phenomenon arises from the restless activity of virtual particles momentarily appearing and disappearing, a subtle dance dictated by quantum mechanics. One of the most compelling ways scientists probe this hidden energy is through the Casimir effect, a force observed between two closely spaced metal plates in a vacuum. This force emerges from the alteration of quantum fluctuations between the plates, resulting in a measurable attraction that reveals the vacuum's tangible influence. By refining techniques to measure the Casimir force with ever-increasing precision, researchers continue to push the boundaries of what we understand about vacuum energy. Advances in micro and nanotechnology have been instrumental in enabling these precise measurements, allowing experimental setups to isolate the subtle forces at play within a nearly perfect vacuum. Recent experiments employ exquisitely sensitive torsion pendulums and atomic force microscopes, instruments capable of detecting forces as faint as a few piconewtons. Through these refined tools, scientists not only verify the existence of the Casimir force, but also explore its dependence on factors such as plate geometry, material properties, and temperature. These nuanced investigations deepen our grasp of how vacuum fluctuations manifest in different physical contexts, bridging the gap between abstract quantum theory and observable reality. Each incremental improvement in measurement precision brings with it the potential to uncover deviations from established theory, which could hint at new physics beyond our current models. The implications of understanding vacuum energy extend far beyond the laboratory scale, touching upon cosmological questions about the universe's expansion and the mysterious dark energy that drives it. By meticulously characterizing quantum vacuum effects at human scales, physicists hope to glean insights that might one day inform our comprehension of cosmic phenomena. Moreover, these experiments underscore the profound truth that empty space is anything but void. It is a seething canvas of energy and potential. As experimentalists continue to refine their methods and theoretical physicists develop more sophisticated frameworks, the dialogue between measurement and theory grows richer. This ongoing synergy promises to illuminate the subtle yet foundational role vacuum energy plays in shaping the very structure of reality. Beyond the Casimir effect, other cutting-edge experimental approaches are emerging, such as precision measurements of vacuum polarization and explorations of the dynamic Casimir effect, where accelerating boundaries can induce the emission of real photons from the vacuum. These phenomena, once considered purely theoretical curiosities, have become accessible frontiers thanks to advances in quantum optics and superconducting circuits. By harnessing these novel techniques, scientists probe the vacuum's response to changing conditions, revealing a richer tapestry of quantum vacuum behavior. Each new discovery not only confirms the intricate predictions of quantum electrodynamics, but also challenges us to rethink the nature of space as an active participant in physical processes rather than a passive backdrop. As we observe the continuous progress in experimental physics, it becomes clear that the quest to measure and understand vacuum energy is a journey of both precision and imagination. The vacuum, once thought to be a simple emptiness, emerges as a dynamic medium filled with subtle forces and energies, inviting us to reimagine the foundations of matter, energy, and space itself. Each experiment, each refinement, brings us closer to decoding the whispers of the quantum vacuum, guiding us along a path toward deeper knowledge of the cosmos. And so, with these new insights in hand, we turn our gaze toward the broader implications of vacuum energy in the grand tapestry of the universe. The concept of vacuum energy, while deeply rooted in abstract quantum theory, opens a window into a realm of possibilities that stretch far beyond traditional science. At its core, vacuum energy represents a vast underlying sea of fluctuating fields that persist even in what we perceive as empty space. This restless activity at the quantum level suggests that space itself holds a form of latent energy, a foundation upon which the fabric of reality is woven. As we begin to understand these fluctuations in greater detail, the idea emerges that tapping into this omnipresent energy might not remain purely theoretical. The notion of extracting usable energy from the vacuum, once relegated to speculative fiction, now inspires serious scientific dialogue. While the challenges are immense, the potential rewards are equally profound, promising a source of energy that is both ubiquitous and, in principle, inexhaustible. Exploring the practicalities of harnessing vacuum energy invites us to consider technologies that could redefine our relationship with power generation and consumption. If methods were developed to manipulate the quantum vacuum effectively, devices could be designed to draw energy from the very fabric of space without depleting conventional resources or producing harmful byproducts. Such advancements might lead to propulsion systems for space travel that do not rely on fuel in the traditional sense, potentially enabling humanity to traverse vast cosmic distances with unprecedented efficiency. Furthermore, the integration of vacuum energy principles into nanoscale technologies could revolutionize computing and communication, leveraging quantum fluctuations to enhance performance or reduce energy costs. Though these prospects remain speculative, they stimulate a vision of technology deeply intertwined with the fundamental nature of the universe, reshaping how we conceive of energy itself. The pursuit of vacuum energy extraction also prompts profound questions about the limits of physical law and engineering. Quantum vacuum fluctuations are inherently subtle and governed by the uncertainty principles that define quantum mechanics, placing natural constraints on the extent to which they can be controlled or amplified. Yet, ongoing research into phenomena like the Casimir effect, where vacuum fluctuations produce measurable forces between closely spaced surfaces, offers glimpses into practical manipulation of vacuum energy at small scales. As experimental techniques grow more sophisticated, the boundary between theoretical possibility and tangible application narrows, encouraging interdisciplinary efforts that blend physics, material science, and engineering. This evolving landscape hints at a future where technology harmonizes with quantum realities, allowing us to harness the very essence of space-time for practical ends. Beyond energy and propulsion, The implications of vacuum energy technologies extend into diverse fields such as medicine, environmental science, and information technology. Imagine medical devices that utilize quantum vacuum principles to operate with unprecedented precision, or environmental systems that mitigate pollution by exploiting subtle energy exchanges at the quantum level. In information technology, quantum vacuum phenomena could enable new modes of data storage or transmission, potentially revolutionizing how information is processed and preserved. While these ideas currently belong to the realm of future possibility, the continuous refinement of our understanding invites a broader contemplation of how vacuum energy might be woven into the fabric of daily life, inspiring innovation that resonates with the universe's most fundamental properties. As we venture further into the exploration of vacuum energy and its practical applications, the journey is as much philosophical as it is scientific. It challenges us to reconsider the notion of emptiness, transforming it from a void into a vibrant source of potential. This shift in perspective not only fuels scientific curiosity, but also expands the horizons of human imagination, encouraging us to envision technologies and possibilities previously unimagined. With each discovery, the quiet hum of the quantum vacuum invites us to listen more closely, to dream more boldly, and to step gently toward a future where the unseen energy of space becomes a partner in the ongoing story of discovery and innovation. At the heart of the quantum vacuum lies a profound challenge to our traditional understanding of existence. For centuries, the concept of nothingness has been synonymous with emptiness, a complete absence of matter and energy. Yet, quantum physics reveals that the vacuum is anything but empty. Instead, it is a seething, restless expanse filled with fleeting particles and fluctuating fields. These ephemeral phenomena constantly emerge and vanish, giving rise to what we call vacuum energy. This revelation invites us to reflect deeply on the meaning of nothing. It suggests that what appears as empty space is actually a dynamic arena of potentiality, a canvas upon which the fundamental forces of nature interplay in subtle and mysterious ways. This philosophical shift urges us to reconsider the boundaries between existence and non-existence, challenging the very fabric of reality as we perceive it. The implications of vacuum energy extend beyond the realm of physics, touching the core of metaphysical inquiry. If the vacuum is not truly empty, then the void itself becomes a source of creation and influence. This idea resonates with ancient philosophical traditions that speak of an underlying unity or energy from which all things arise. Modern science, through the lens of quantum mechanics, offers a new language and framework for these age-old contemplations. The vacuum's restless energy hints at a universe that is far more interconnected and alive than classical physics once suggested. It encourages a vision of reality where emptiness is not mere absence, but a fertile ground for emergence and transformation. Such a perspective opens pathways to integrate scientific understanding with broader reflections on being, existence, and the continuous unfolding of the cosmos. and philosophical reflection, the recognition of quantum vacuum energy alters how we conceive space itself. Space is no longer a passive backdrop, but an active participant in the cosmic drama. Its properties influence the behavior of particles, the expansion of the universe, and the subtle forces that govern physical phenomena. This dynamic nature of space challenges classical intuitions and invites a more nuanced appreciation of the universe's complexity. It suggests that the void is imbued with structure and influence, a medium through which energy and information flow invisibly and incessantly. Embracing this view allows us to approach scientific questions with renewed curiosity, seeing space not as nothing, but as a vibrant and essential component of reality's tapestry. As we delve deeper into the mysteries of the quantum vacuum, we find ourselves at the threshold of redefining what it means to exist. The boundaries between something and nothing blur, revealing a continuum rather than a binary distinction. This insight encourages a humility in our quest for knowledge, reminding us that the universe often defies simple categorization. The vacuum's subtle energies hint at layers of reality that remain hidden from our everyday perception, urging us to remain open to wonder and discovery. In embracing the enigmatic character of the vacuum, we also embrace the mystery at the heart of existence itself, an invitation to ponder the infinite possibilities that lie within the fabric of space. Despite the elegance of our current understanding of quantum vacuum energy, many profound challenges remain. One of the most striking puzzles is often called the vacuum catastrophe, an immense discrepancy between theoretical predictions and observed values of vacuum energy density. Quantum field theories suggest that the vacuum should teem with enormous amounts of energy. Yet, astronomical observations indicate that the vacuum's energy is incredibly small. This contradiction is not merely a numerical curiosity, but a fundamental riddle that lies at the intersection of quantum mechanics and cosmology. It invites us to question the completeness of our models and to consider that perhaps our grasp of space-time and energy remains incomplete. The vacuum catastrophe reminds us that nature's underlying workings are subtle, and the answers we seek may require new physics beyond our current frameworks. Another open question concerns the nature of vacuum fluctuations themselves. These ephemeral blips in energy, arising spontaneously from the quantum vacuum, challenge our classical notions of emptiness. Yet, we still strive to understand how these fluctuations influence the large-scale structure of the cosmos and the forces that shape it. For instance, vacuum fluctuations are thought to play a vital role in phenomena like the Casimir effect, where forces emerge between uncharged, parallel plates in a vacuum. But extending this understanding to cosmological scales, where vacuum energy might drive the expansion of the universe, remains an ongoing pursuit. The interplay between the quantum vacuum and gravity, as described by general relativity, is one of the most delicate and profound frontiers in physics today. It is here that the fabric of space reveals its deepest secrets, slowly unfolding to those patient enough to explore its subtle whispers. quest to comprehend the vacuum also raises fundamental philosophical questions about the very essence of space and nothingness. Is empty space truly devoid of substance, or is it a dynamic stage filled with restless energy and potential? Modern physics suggests the latter, yet the conceptual shift required to embrace this view is profound. Scientific inquiry into the vacuum's properties challenges us to rethink the meaning of existence and the role of observer and measurement in shaping reality. Moreover, the vacuum may hold clues to the unification of forces, hinting at a deeper symmetry or principle that underlies all physical phenomena. Such ideas propel theoretical research forward, inspiring new hypotheses and experimental probes that push the boundaries of what we can measure and understand. This ongoing dialogue between theory and experiment enriches the tapestry of knowledge, even as many threads remain unresolved. In exploring these deep challenges, we are reminded that science is not a collection of fixed truths, but an evolving journey. Each discovery uncovers new questions. Each answer reveals further mysteries. The physics of nothing teaches us humility and patience, encouraging us to embrace complexity and uncertainty as inherent parts of the cosmic story. As researchers continue to refine their models and devise ingenious experiments, the horizon of understanding expands, promising insights that may one day illuminate the vacuum's secrets more fully. Until then, the vacuum remains an enigmatic frontier, a silent expanse inviting curiosity and wonder. This openness to the unknown nurtures the spirit of exploration that drives science ever onward. When we speak of nothing, it is tempting to imagine a simple void, an absence devoid of substance or activity. Yet, the quantum vacuum challenges this intuition profoundly. At the smallest scales, what appears to be empty space is in fact a seething ocean of fluctuating energy, where pairs of particles and antiparticles spontaneously emerge and vanish within instants too brief to measure directly. This restless activity, often described as quantum vacuum energy, suggests that space itself possesses intrinsic properties far from inert. These fluctuations give rise to subtle forces, such as the Casimir effect, where two uncharged plates in a vacuum attract each other due to changes in vacuum energy between them. The vacuum, then, is not a mere backdrop, but an active participant in the physical world, influencing the behavior of particles and fields that dance upon its stage. Such insights compel us to reconsider our notions of emptiness, revealing a cosmos where even the void hums with dynamic potential. Beyond the ephemeral flickers of virtual particles, the vacuum's energy may hold the keys to some of the universe's deepest mysteries. Cosmologists posit that this pervasive vacuum energy could be connected to dark energy, the mysterious force driving the accelerating expansion of the universe. Although the exact nature of this connection remains elusive, it underscores the vacuum's profound influence on cosmic scales, linking the infinitesimal quantum world to the vastness of space-time itself. Moreover, the vacuum's structure is intimately tied to the fabric of space, affecting how forces propagate and how particles acquire mass through mechanisms such as the Higgs field. In this light, the vacuum is not an empty container, but the very medium that shapes the laws of physics, a silent architect of reality's architecture. Understanding this subtle interplay invites us to explore how nothingness is imbued with everything that gives rise to existence. The journey to comprehend the physics of nothing is ongoing, marked by both remarkable progress and enduring enigmas. Experiments in particle accelerators and precision measurements continue to test predictions about vacuum fluctuations and their consequences. Theoretical frameworks such as quantum field theory and general relativity strive to unify the vacuum's quantum properties with the classical geometry of space-time, a quest that has inspired proposals like quantum gravity and string theory. Each step forward reveals layers of complexity, suggesting that the vacuum is a dynamic and structured entity rather than a simple emptiness. This evolving understanding reflects the broader nature of scientific inquiry, a continuous unfolding of knowledge that transforms apparent voids into realms rich with structure and meaning. As we deepen our grasp of the vacuum, we glimpse the profound connection between the microcosm and the macrocosm, where nothing and everything converge. Reflecting on these insights, we appreciate how the notion of nothing has transformed from a philosophical abstraction to a tangible subject of scientific study. Far from being a mere absence, the vacuum is a dynamic, vibrant medium suffused with energy and potential. It challenges our perceptions, inviting us to rethink what it means for space to be empty. This evolving perspective enriches our understanding of the universe's origin, structure, and fate, illuminating the subtle forces that permeate all of reality. The quantum vacuum stands as a testament to nature's capacity to surprise and inspire, revealing that emptiness itself is a canvas painted with the brushstrokes of fundamental physics. Such revelations encourage us to look beyond appearances, to seek the hidden depths within what seems to be void. In contemplating the physics of nothing, we embrace a profound paradox, that from what was once thought to be emptiness arises the complexity and diversity of existence. The vacuum, once dismissed as inert, is now understood as a fertile ground for the genesis of particles, forces, and even the structure of space-time. This recognition invites a sense of wonder and humility, reminding us that the universe holds secrets woven into its very fabric. As ongoing research continues to probe these mysteries, the boundary between nothing and everything blurs, revealing a cosmos where absence and presence are intertwined in delicate harmony. This ever-expanding horizon of understanding beckons us forward toward new questions and discoveries yet to come. As we reflect on the subtle forces at play within the vacuum of space, it becomes clear that what we once considered empty is, in truth, a dynamic arena of energy and potential. Quantum vacuum energy, the restless sea of fluctuating particles and fields, permeates all of space, quietly influencing the cosmos on scales both vast and minuscule. This hidden energy contributes to the very expansion of the universe, a gentle yet persistent push that shapes the grand architecture of galaxies and cosmic voids. It is a reminder that beneath the stillness of the night sky lies a restless vitality, a silent symphony of forces that sustain the universe's ongoing story. As we continue to investigate these unseen energies, we are invited to reconsider our place within this vast, interconnected whole. A universe where even nothingness holds the power to create and transform. The properties of space itself reveal a remarkable tapestry woven from quantum fields and fluctuations. Far from being a passive backdrop, space emerges as an active participant in the unfolding drama of existence. The quantum vacuum challenges our classical intuitions by demonstrating that emptiness is never truly empty, but a seething matrix of possibilities. This perspective reshapes our understanding of reality, hinting at a cosmos where the line between void and substance is fluid and ever-changing. The delicate balance of vacuum energy influences phenomena from the smallest particles to the grandest cosmic structures, underscoring the unity of nature's forces. In embracing this vision, we find humility in the face of complexity and inspiration in the quest to uncover the universe's deepest truths. Ultimately, the physics of nothing invites us to marvel at the universe's quiet energy, a force that is both hidden and essential. It whispers through the fabric of space-time, knitting together the cosmos in ways that challenge our imagination and deepen our sense of wonder. This subtle energy, pervasive yet elusive, reminds us that the essence of reality is far richer than our senses alone can perceive. As science advances, unveiling the mysteries of quantum vacuum energy and the nature of space, it also illuminates the profound interconnectedness of all things. In this gentle unfolding, we find not only answers, but also new questions, a testament to the boundless curiosity that drives human discovery. In closing, we are left with a profound appreciation for the quiet, powerful forces woven into the very fabric of existence. The physics of nothing reveals a universe alive with potential, where emptiness itself is a wellspring of energy and creativity. This awareness invites us to look beyond the visible, to sense the subtle dance of particles and fields that shape our reality. It encourages a reverence for the cosmos that transcends the tangible, inspiring awe at the delicate harmony sustaining all that is. Thus, in contemplating the universe's quiet energy, we embrace a vision of reality that is at once mysterious, beautiful, and deeply interconnected.